Now we are going to discuss solubility. So let's see, we have a solute A which we are being dissolved in solvent B. So we add a little bit of A in solvent B and then we shake the flask vigorously, okay, until this A is dissolved completely. If it is going to dissolve, I mean there might be a case that we keep on shaking the jar and it's never going to dissolve. There are solute which is not going to dissolve in a given solvent B. So okay, but let's assume in this case A is going to dissolve completely in B. Now we keep on adding A little by little and keep shaking the flask and keep on repeating until we reach a point. If we add a little bit more of A, it doesn't dissolve in B. So if we add any more of A, it's not going to dissolve in B, it's just simply going to precipitate out, it's just going to settle at the bottom of the flask. So we have reached the maximum concentration of solute A in solvent B. So the maximum amount of solute A which dissolve in solvent B without precipitating out is the solubility of solute A in solvent B. So basically this is the maximum concentration attainable of solute A in solvent B, that is called solubility. So there are salt which is very highly soluble and there are salt which is very low, has a very low solubility in a given solvent. For example, NaCl in water. We know it is highly soluble. In fact, little less than 400 gram of NaCl can be dissolved in 1 liter of water. On the other hand, we have silver chloride, only a few milligram, around 1.9 milligram of AgCl can be dissolved in 1 liter of water. If I add anything more than 1.9 milligram of AgCl in water, in 1 liter of water, it will simply precipitate out. It will simply settle at the bottom of the flask. The solubility depends upon the nature of solute and solvent. It depends upon the interaction between among the solute molecule, between solvent molecules, and between, most importantly, between solute and solvent molecules. Okay, let's try to understand it. Let's see it briefly. Okay, so we have already seen NaCl. So NaCl and sugar, they easily, readily dissolve in water. But another example, anthracene does not dissolve in water at all, but it readily dissolves in benzene. So if we try to understand the interaction, NaCl is ionic, goes into the solution and dissociate as ion, it becomes Na plus and Cl minus, gets solvated by water, which is polar, and that's how it has a very high solubility. Sugar, it has hydrogen attached to oxygen and that leads to hydrogen bonding. Again, water has lots of hydrogen bonding. And so sugar becomes part of this hydrogen bonding network, and that's how sugar gets dissolved in water. Anthracene, it is nothing but a hydrocarbon. No ionic character, no hydrogen bonding, so there is no mechanism which will help him to dissolve in water. It's basically non-polar. Benzene, This is also non-polar. It's exactly like anthracene. Both of them are hydrocarbons. So, this anthracene dissolves in benzene, but doesn't dissolve in water. So, we can conclude this polar solute dissolve in polar solvent and non-polar solute dissolve in non-polar solvent. We can say like dissolves like. When solute is added to solvent, the concentration of solute increases, and that is called dissolution. But at the same time, another process is going on. The solute molecules or solutes are going to hit the other solute solid, and in this process there might be some crystallization and they comes out of the solution, and that is called precipitation. And these two processes are happening all the time. So, we are having solute plus solvent, and we are getting solution. So, in the forward direction the dissolution is happening, and in the backward direction precipitation is happening. And then there is a dynamical equilibrium. So, at the rate at which solute goes into the solvent, or the rate the solute comes out of the solution, when the two rate becomes equal, then we have equilibrium. And as we keep on adding solute, we reach to a stage when solute going to the solvent is no longer feasible, and we have no more dissolution, and at that time we reach to the maximum concentration of solute possible, and that is called saturated solution. Saturated solution is when the solute has reached its maximum concentration. We cannot add any more solute in the solution. If we add more solute, the solid solute in the solvent or the solution, it will simply not dissolve, it will simply come out from the solution. At this stage, we can say that solution has saturated with the solute. We cannot increase the concentration of solute anymore. Okay. So, now we have to discuss the effect. So, this is a reaction, we can treat it as a reaction, and it should follow what is called Le Chatelier principle. Le Chatelier principle. So, we can study the effect of pressure and temperature on this reaction, on this dynamical equilibrium. Okay. Let us say solute is, let us discuss first solid and liquid, where solute is solid and solvent is liquid. And what would be the effect of pressure? There is not going to be a much effect of pressure, because most of the solid and solvent is usually very highly incompressible. So, if we increase the pressure, there is no any change in the volume change in of the reaction material. So, there is not going to be much change in the direction of the reaction due to the pressure change, but temperature change would have a lot of effect if there is a enthalpy is involved, delta H. If this reaction is exothermic, that is delta H is negative, that means as the reaction goes forward, the heat is liberated, we are getting energy. So, increase in the temperature will take the reaction in a backward direction, because it want to minimize the the effect of we are having due to the temperature increase if the reaction goes forward, if the delta H is liberated, the system has more heat, so the temperature would increase. But the researcher says the reaction will move in a direction where the stress can be minimized. So, it has to move in a direction where the heat is absorbed by if we increase the temperature. So, it is clear that for delta for exothermic reaction, reaction will go backward, will move in the backward direction. From the same logic, we can now conclude if delta H is greater than 0, that need energy to move the reaction, energy is absorbed to move the reaction forward, reaction is endothermic. Then the reaction will move forward. Okay. Now, that about a solid dissolved in liquid. Okay. Let us now consider a gaseous solute is being dissolved in a solvent, liquid solvent. Now, same observation can be made by Le Chatelier principle. If the reaction is delta is exothermic, that is delta H is less than 0, reaction goes backward. If delta H is greater than 0, reaction is endothermic, reaction goes forward. But in this special case, let us consider A, which is gaseous, goes to a liquid. This is a condensation. We know to going from liquid to gas, that is basically boiling, we need energy. So, going from gaseous to liquid, the gas energy will be evolved. So, this reaction is exothermic and delta H is less than 0. So, we can say as the temperature is increased, solution the reaction will go backward, that is the solubility of gas in the solution decreases as we increase the temperature. Okay. Now, let us think about the pressure. So, this is my vessel where I have my solution. In this case, we have the solute particle, and this is the solute particle in a gaseous phase. And this is a closed flask, and I have some pressure applied on the system. Now, if pressure is increased, what is going to happen? The solution being highly incompressible, it does not compress, but gas will compress. And now, I have more gaseous particle stored in a smaller volume. So, what the Le Chatelier will say? To reduce the stress, we have to go in a direction that it can reduce the stress. So, of course, this solute particle which has a concentration has increased in this region, even though the concentration in this remain constant because not compressible. So, this will start going into the solution to reduce the effect of stress. And it is very clear that as we increase the pressure, solubility of gaseous solute increases in solution. And this has been formulated, is given a mathematical expression for this the solubility of gaseous particle in concentration of gaseous solute in the solution by Henry, and the law says P is equal to KH x, where P is the pressure of the solute over the solution, x is the concentration of solute in solution. So, as the pressure increase, the mole fraction, the concentration of solute increases. and it's clear, we can put it the other way around, P divided by Kh, higher the Henry constant, lesser the solubility of gaseous solute in solution. Okay, let us next discuss vapor pressure of liquid solution. So, let us first consider the pure liquid. Let us say I have a liquid A, put it in a closed flask. So, I have introduced some liquid over here. This is a volatile liquid. So, at this given temperature, some of this liquid molecules is going to escape and they are going to go into this empty space. Now, these gaseous molecule of this same liquid is moving around and they are going to hit back the surface, and some of them can start going back into the liquid form. So, there is some kind of a process is going on where liquid A goes to gaseous and then this gaseous comes back. So, there is a reaction going forward and reaction coming backward, and there is a dynamic equilibrium, and at the equilibrium the pressure, this liquid this gaseous molecule of that same liquid A is going to exert some pressure on this surface, and that pressure is called the vapor pressure, and that we put 0 due to this a pure one. And same thing is going to, if we have another evacuated flask and there we put this liquid B, same thing is going to happen, is going to fill up this empty space, and then again we are going to have a dynamical equilibrium, and this gaseous molecule is going to exert the pressure on the surface, and this is going to call PB 0, the vapor pressure of pure B, pure liquid B. Okay, and of course, in this I have considered this is evacuated flask. So, only pressure is going to be due to this gaseous molecule of B, and same thing here, the pressure is going to be due to only the gaseous molecule of liquid A. Now, let us mix them together. Now, we are going to mix them together. Now, we have A plus B here, and same thing A plus B. We have A and solution of A and B in liquid form, and gaseous A and B in gaseous form. And now, there should be some relationship between these, what is the pressure exerted by A, what is the pressure exerted by B, and what is the total pressure T. So, this is the partial pressure due to A, partial pressure to B, and this is the total pressure. That is how I can classify the gaseous phase. But what about the liquid phase? Liquid phase I can classify by mole fraction of A, mole fraction of B. So, once we have classified what is the relationship between these quantity, and this is given by Raoult's law, says that this P A is proportional to X A, P B proportional to X B. We also know when X A equal to 1, that is when we have a pure liquid A, then P A is equal to P A 0. and x b is equal to 1, then we have P b is equal to P b 0. So, we get the proportionality constant immediately, and I can write this equation in this form. So, let us look at this in this diagram. What I am plotting is the pressure, partial pressure of A and B, this is a mole fraction. So, over here we have a mole fraction x A is equal to 0 and x A is equal to 1, and same way over here we have x B equal to 0 and x B equal to 1. So, when we have a pure B, the partial pressure due to partial pressure of B is going to be P b 0 and partial pressure of A is going to be 0. What about when we have a pure liquid A, then the partial pressure of A is going to be due to the P A 0 and partial pressure of B is going to be 0. And one can see that this is a straight line. As I change x A, P A is going to linearly change. So, if I am going to change x A from 0 to 1, the partial pressure of A is going to increase linearly. Sorry, this is going to make a straight line. Okay. And same thing when the partial pressure, when we have a pure liquid B. So, as the concentration of B is increasing, the partial pressure of B also will increase, would have a straight line, and we get this straight line. What about the total pressure? Okay. The total pressure we can calculate from this equation. So, total pressure is P A 0 x A plus P b 0 x b, and I can substitute x b is equal to 1 minus x A. So, we get P A 0 x A plus P b 0 1 minus x A. So, I get P b 0 plus P A 0 minus P b 0 x A. So, this is again a linear function with respect to concentration in A, and of course, we are going to get this straight line, which is really a sum of these two lines. This is the P total, this is this is partial pressure of A, this is the partial pressure of B, and this is the P total, which is P A plus P B. Okay. So, that is how the solution would behave. Let us do a example given in the book. Let me read it out. Let me clear the blackboard first. Okay. Let us do the example from the book. It says, the example is as follows: vapor pressure of chloroform and dichloromethane at 298 Kelvin are 200 millimeter Hg and 415 millimeter Hg respectively. Okay. So, we have chloroform CHCl3, let us call that A. We have dichloromethane CH2Cl2, let us call that B, and we are given vapor pressure of these of the pure components of P 0. So, P A 0 is going to be 200 millimeter Hg, and Pb0 is going to be 415 millimeter Hg. Okay. Okay. Now, number 1, calculate the vapor pressure of the solution prepared by mixing 25.5 gram of CaCl3. So, we are mixing 25.5 gram of this and 40 gram of liquid B. And we are asked the vapor pressure of A and B and the total vapor pressure. Okay. So, what is the let us go back to the basic, and the formula is PA0, PA is equal to XA PA0, PB is XB PB0. Now, PA0 and PB0 is given. This is PA0, this is PB0, and so I need mole fraction XA and XB. How is the XA and XB is defined? XA is NA divided by NA plus NB, and same way I can calculate XB, and also I can calculate XB simply by 1 minus XA. Now, to calculate Na, I need the molecular weight. Okay. So, let us see what is the molecular weight of Molecular weight of CaCl3 is 119.5 and molecular weight of CH2Cl2 is 85 gram per mole. And then we can calculate Na, number of moles of each. So, that would be 25.5 gram divided by 109.5 gram per mole, that will give me moles of CaCl3, that is A. So, let us do that. 25.5 divided by 119.5, and answer we are going to get is 0.213. And same thing we need to do for B, that is dividing 40 by 85. 40 divided by 85, and answer I am going to get is 0.470. And now, I need to calculate simply XA mole fraction. So, it is all given there. Na is 0.213 divided by Na 0.213 plus 0.470. So, using calculator, 0.213 divided by 0.683, I get answer 0.312. And of course, using this formula 1 minus 0.312, I get 688. Now, I have all the information required. The PA would be given by XA, we have calculated 0.312 multiplied by PA0, which is given right here 200. So, I get 62.4, and the PB, okay, XB is given here 0.688 multiplied by 415. Answer I am going to get is 0.688 multiplied by 415. Answer is 285.5 millimeter Hg. And of course, the total pressure would be simply sum of these two quantities. So, the total pressure is going to be 347.9. So, that is the total pressure. So, we have calculated part A. Now, it is asking mole fraction of each component in vapor phase. Mole fraction of each component in vapor phase. Now, we know this ideal gas law, we are going to apply that P v is equal to N R T. Okay. And if it is a partial pressure, then P A N A R T. So, we need to calculate mole fraction of A and B in vapor phase. So, mole fraction would be, let us call that capital X A, that will be, okay, I have already used N. So, let us put vapor, okay, over here. So, N A in vapor divided by total moles, N A in vapor plus N B in vapor. And if I substitute N A from here, the answer would be simply I will get P A divided by P A plus P B. And I have all this information. P A is given right here, P B, and P A plus P B is nothing but P total. So, I get mole fraction of A in vapor phase, and that would be 62.4 divided by 347.9. So, let us see 62.4 divided by 347.9. So, 0.179. And what about X B? That would be 1 minus X A. So, I get 0.821. Okay. So, we have calculated mole fraction of A and mole fraction of B in solution, mole fraction of A and mole fraction of B in vapor. One thing to notice is this: the vapor has become richer in B. See, in the liquid phase, the mole fraction of B was 0.688. Now, the mole fraction of B in vapor phase has become 0.821, and that has something to do with the volatility. And you can see V has a higher vapor pressure, means it has a higher tendency to go into vapor phase. It has a higher volatility. So, it is a volatile compound, more volatile compound than A. So, it has a higher tendency to go into the vapor more than A. So, it is going to be richer in vapor phase than A. Okay. Okay, let us do one more problem from the in text question. Okay, let me clean the blackboard first. The vapor pressure of pure liquid A and B are 450 and 700 millimeter Hg respectively. So, we have A and B and P 0. The P A 0 and P B 0 is 450 and 700 millimeter Hg. 450 and 700 millimeter Hg respectively. So, vapor pressure of pure A is 450 millimeter Hg, vapor pressure of pure B is 700 millimeter Hg. Now, of course, at 350 Kelvin, find out the composition of liquid mixture if total vapor pressure is 600 millimeter Hg. If Pt is 600 millimeter Hg, find the composition of liquid mixture. Also find the composition of vapor phase. Okay. Now, let us first assume in the liquid phase the mole fraction of A is X A. Then of course, the mole fraction of B is going to be 1 minus X A. Okay. The vapor pressure, once I have mole fraction assumed, I can write the vapor pressure of A and B in terms of X A. So, that is going to be 450 X A, the vapor pressure of A is 450 X A and the vapor pressure of B is going to be 701 minus X A. And the question tells me the total pressure. So, that is this plus this equal to this. So, I have a one equation that is 450 X A plus 701 minus X A, one equation, one unknown, solve it and we have the answer. So, let us try to solve it. What we will get? 450 X A plus 700 minus 700 X A. So, that is 700 minus 250 X A. Bringing to the other side, dividing by 250, I am going to get X A is equal to 100 divided by 250. So, that is 0.4. So, we have found that X A is 0.4. So, pressure, the partial pressure of A is going to be simply 450 into 0.4, that is going to be 180 and partial pressure of B is going to be 700 multiply 1 minus X A, that is 0.6. So, it is going to be 420. So, we can check the total pressure is 180 plus 420, that is 600 millimeter Hg. Now, in the part B, the same question is also find the composition of vapor phase, and in the last example we have already seen the composition of vapor phase. We can calculate the parts from the partial pressure. The composition of vapor phase is X of vapor phase. Okay, let me clear the blackboard a little. So, composition of in vapor phase of A is simply partial pressure of A divided by total pressure, and answer is straightforward, divided by 600 and I get 0.3. I can calculate the mole fraction of B in vapor pressure either by 1 minus 0.3 and I can try that one also just for checking. 420 divided by total pressure, that is 600.7. I get same answer by using both the method, and I have completed this task starting from the very basic principle. Okay, so, next topic which we are going to discuss is vapor pressure of solution of solid in liquid. Solid in liquid. Okay, let us examine the Rod's law one more time. What it says? It says P A, the partial pressure of one component, let us say component A is equal to X A P A 0, and same thing P B is equal to X B P B 0. So, if I have a solid, what is the vapor pressure of it? For most of the solid, it is going to be negligible. This solid is usually not volatile. I am considering that there are some solid which of course have a they evaporate and they would have some vapor pressure, but for most of the solid there is no vapor pressure. So, if I leave this solid, it is not going to evaporate. If I leave let us say alcohol or liquid, it is going to pretty much evaporate after some time, but if I leave the solid in let us say this table or metal object, it is not going to evaporate in my lifetime. So, of course, there are some solid which will evaporate, but most of them not. In such cases, the P b 0, let us say this is A is the solvent, B is the solute, solute. Then in that case, P b 0 is going to be 0. So, this is going to be 0. So, Raoult's law in general it says any solution, for any solution the partial vapor pressure of each volatile component in the solution is directly proportional to its mole fraction. In this case, the vapor pressure is going to be due to only the solvent A, because it is going to evaporate in time, but B, the solute is not going to not going to give any component, it is going to be the pressure is going to be 0. So, all the pressure is going to come from the partial pressure of A. Okay. And this can be understood also by this following diagram. So, we have solvent, pure solvent, and it is going to, it is in a closed evacuated flask. So, in this flask we have only this A, this solvent A, and it is going to evaporate and is going to filled up this whole. So, this is a gas and this is liquid of A, and the equilibrium which is going to happen is from this surface there are some gaseous molecule which is going to strike the surface and going into the solution, and from this surface some of them is going to have enough energy to escape. Okay. Now, if I add a solute to this, what is happening? There are some molecule of solution of the solvent and there are some molecule of solute. So, the concentration of solvent molecule at the surface has decreased. Of course, solute is not going to evaporate, that is what we have considered, these are not volatile at all. That is the assumption here, which is true in most of the cases, but the solvent is going to evaporate, but there is a lesser number of solvent molecule at the surface. So, the evaporation has decreased. The moment we have added the solute, the concentration of solvent molecule at the surface has decreased, but this is has not changed. Let us consider that is not the concentration of or partial pressure of A has not changed. So, it is going to strike at the same rate. So, evaporation rate has decreased, but the condensation rate has not changed. In that case, there is going to be more condensation than the evaporation, and as the condensation has increased. So, partial pressure of A is going to decrease, and we are going to reach to a new equilibrium where the partial pressure of A is going to be less than what it was, and that can be understood again from this, because since in the pure solvent there is no solute, X A is 1. So, P A is equal to P A 0, and as the X A has become less than 1, P A has become less than P A 0, and the exact relation is given over there. Okay. Next, we are going to discuss ideal solution and non-ideal solution. So, what makes a solution ideal? So, if a solution follow the Raoult's law over the whole range of concentration, then this solution is called ideal solution. But question is, what makes them to follow the Raoult's law? And that is where comes the two very important quantity. Those are delta V of mixing and delta H, the enthalpy of mixing, and they should be 0. So, if I mix let us assume if I mix 1 liter of solvent A plus 2 liter of solvent B. If the total volume after mixing is 3 liter of solution, then it follows the condition 1. And the second condition is if no heat is evolved during the mixing, that is if the temperature does not change after the mixing, then it is a ideal solution. I mean, during the chemistry experiment, I am sure you must have observed if I mix water with concentrated H2SO4, the mixture becomes quite warm. That is delta H of mixing is non-zero. It is a exothermic reaction. If the total volume is greater than or less than 3 liter, or there is a heat is involved, then this solution is non-ideal. Okay. Let us try to understand this with a simple diagram. Let us see if I have a solvent A in a container, and on the this vapor and liquid boundary zone. Right now, I have only solvent A. Now, to that I am going to add B, but before hand let us try to understand what is happening. So, there is an interaction between A and A. If it is a pure solvent A, now I am going to add solvent B. So, some of the A molecule at the boundary will be replaced by another solvent B. It could be solvent or it could be solute. If you are mixing let us say 50% of water and ethanol, then these are two solvents which we are mixing. If I am mixing let us say sodium chloride in water, then sodium chloride is going to be solute and water is a solvent. So, it is a now, so there is a solvent A and somewhere in between is solvent B. It could happen very often if there is depending on the concentration. Now, initially in the pure solvent A had an interaction between A and A. Now, once the another solvent or solute is added B, then we also have a interaction A and B, and they could have a interaction B and B depending upon the concentration. Now, this A and A interaction could be stronger than A B interaction. What would happen? So, initially right instead of this there was A and A, and that interaction is stronger than A B interaction. So, A and A interaction is stronger and A B interaction is weaker. So, we have replaced a stronger interaction with a weaker interaction. Now, this molecule A is lesser stable. So, it has a higher tendency to go into vapor phase. It requires a lesser amount of energy, lesser push to go into the vapor phase. So, what would happen? It is become the vapor pressure will increase. So, okay, let me draw this diagram which I have drawn earlier. So, that is what we are changing is mole fraction of A. Over here x A is 1, over here x A is 0. So, vapor pressure of A is going to be this. Let us say this is P A 0, and same thing if x B over here is 0 x b is over here 1 and we get another line. This is vapor pressure of B. This we have done earlier and this is P b 0 and the total pressure is going to be this. This is the ideal solution. But now, A interaction is stronger than A B interaction and the B molecule has interrupted this stronger interaction and replaced with a weaker interaction. Now, this A can go into the vapor phase easily and that is why increasing the total pressure or individual vapor pressure. So, now we have a what is called positive deviation. So, if A interaction is stronger than A B interaction, then we have positive deviation. Okay. And other way around, if A interaction is weaker than A B interaction, then we have negative deviation. So, in this diagram for a positive deviation, the total vapor pressure has changed into the positive direction and same way the individual component also would change in the positive direction. And for a negative deviation, where interaction between A and B is stronger than A and A, we are going to have a deviation in another direction and that would lead to negative deviation. Okay. Let us look at the example, ethanol and acetone. Ethanol C2H5OH, acetone CH3COCH3. So, this molecule in a solution has a lot of hydrogen bonding. In a liquid phase, it is going to have a lot of hydrogen. There is a polar hydrogen is available there. So, it is going to lead to hydrogen bonding and there is no such interaction in acetone. So, now when there is only ethanol present, there is a strong A and A interaction due to hydrogen bonding. And now, when I add acetone to it, this hydrogen bonding network is interrupted. So, this molecule becomes molecule A, that is ethanol, becomes lesser stable and it has a higher tendency to go into the vapor phase and it leads to positive deviation. Let us look at the other example, that is between chloroform and acetone. So, acetone that is CH3COCH3 and chloroform that is CCl3H. Now, we can see that there is no hydrogen bonding within acetone or within chloroform. But once we put them together, there is hydrogen bonding between this oxygen and hydrogen, as there is a very powerful electron withdrawing group over here. So, it will withdraw all the electron density, making it quite polar and now they can have a hydrogen bonding. So, that will lead to stronger interaction. So, there is a stronger interaction between A and B and as we have discussed, that will lead to negative deviation. So, we can see by looking at the interaction between the components, we can kind of guess that in which direction the vapor pressure would change, whether it is going to be a negative deviation or positive deviation. Okay. When we have a very large deviation in a binary solution, then they form what is called azeotrophs. Okay. So, we have seen earlier the vapor phase is usually richer in more volatile solution, richer in more volatile component. And using this property, one can devise a way to separate these two components just by heating the solvent solution, collecting the vapor which is richer in volatile component, condensing it back, again heating it, and the vapor which we are going to get from this condensate is going to be even richer in volatile component, and if we keep on doing it, should be able to separate out the two components. But azeotrope is a special kind of solution where the liquid phase and the vapor phase has same concentration of liquid phase and vapor phase. And it is clear, if there is no difference between concentration of liquid phase and vapor phase, if I just collect the vapor phase, it is going to give me the condensate is going to give me the same concentration as liquid phase, and it cannot be I cannot separate A from B. So, we have already discussed weaker interaction between two components compared to interaction between component A and or component B leads to positive deviation. That is, it has higher vapor pressure than it will be if I calculate the vapor pressure using Raoult's law. We know if higher the vapor pressure, lower the boiling point. Higher vapor pressure means more volatile component, more volatile, lower the boiling point. So, in this case, weaker interaction, positive deviation, that means higher vapor pressure than calculated by Raoult's law, and it will leads to minimum boiling azeotrope. And similarly, if we have a stronger interaction between A and B compared to interaction between A and A or B and B, then we have a negative deviation that is the vapor pressure is lower than what it will be if calculated using Raoult's law, then we are going to get maximum boiling azeotropes. And the example for such kind of a binary solutions are, if I have 95% ethanol by volume in water, it forms minimum boiling azeotropes. And similarly, if I have 68% HNO3 by weight in water, then it forms maximum boiling azeotropes. So, that is where we stop. Thank you very much.